So let's talk about orbits. So I pulled this picture from one of the concept questions. Again, this was a thought process that Galileo went through, and I'm sure many others as well. If we were at the top of Mount Everest, assuming no air, just so that we can assume there's no drag, as the object is launched, so it's given a velocity. If we rewind way back earlier in the semester and we talk about projectile motion, I know an object that has been thrown maintains its horizontal velocity, but because of the acceleration of gravity, it ends up going through projectile motion and falls to the ground. If I launch faster, it maintains that same horizontal velocity, so it ends up going farther. So the thought process behind this is, okay, well, if I launch something, it goes through this projectile motion, so it's moving parallel to the ground as well as falling towards the surface of the earth. If I launch faster, it can go farther. But because of the curvature of the earth, essentially there should be some sort of launch speed that as it moves parallel to the surface of the earth, as well as falls, the curvature of the earth makes it such that the object never ends up hitting the earth. And so we end up with, it's essentially a form of projectile motion, but the Earth's surface, of course, not being perfectly horizontal, not having a flat Earth, we end up with motion around the Earth. And so we end up with something that orbits the Earth. So an example, the Earth, well, there's many examples, really. We know the moon orbits the Earth. So the moon, it has a velocity. As it is moving with that velocity, it is getting pulled towards the Earth. And the Earth, of course, is not in the way. Oh, that's not a very good circle. Please forgive me for that. So even though the moon is incredibly far away, there is still the pull of gravity. We could calculate this force of gravity that the moon experiences, the attractive force of gravity towards the Earth, by going back to G. We would need the mass of the Earth and the mass of the moon. And then the table in the test notes gives us the average distance between them. So we've been calling that R. I'll grab that off the test notes here in just a sec. Well, let me go get that. So when I go to the test notes and look at the moon, the line for the moon, the mass of the moon is 7.36 times 10 to the 22nd kilograms. The second column is labeled at the top as the mean distance from the sun, but there's a superscript of a B, which you look at the bottom, and it tells you for the moon, the distance that is given is actually the average distance between the moon and the Earth. So the value we have, 3.84 times 10 to the 8th meters. So average distance between moon and Earth. We need the mass of Earth, which I pulled as well, 5.98 times 10 to the 24. And then big G, our constant, 6.67 times 10 to the negative 11 Newton meter squared over kilograms squared. Okay, I'm not going to rewrite them all because that's a lot of writing. They're all right next door. So I'm going to go ahead and plug these values in to find the force of gravity on the moon due to the Earth. Okay, I'm getting 1.99 times 10 to the 20th newtons. Now, conceptually, I have no real grasp of force of gravities when we're talking about these astronomical distances. It's big. I would expect the force to be big. Let's talk about G, meaning the acceleration of the moon. Now, specifically, the acceleration due to gravity of the moon towards the Earth. I can either calculate that using big G, mass of the Earth, radius of the orbit squared, or I can go ahead and just take the force of gravity we just calculated and divide by the mass of the moon. The acceleration of gravity that the moon experiences towards the Earth is independent of its own mass. It's due to the Earth. When I divide by the mass of the moon, I'm getting 0.0027. This would be in meters per second squared. This is 2.7 millimeters per second squared. That's incredibly small. But this acceleration is what causes the moon to go through the projectile motion. So both continue traveling horizontally, or not horizontal, but parallel to the Earth, as well as falling towards the Earth, which essentially puts the moon in a state of free fall around the Earth. Now, the Earth experiences the same force of gravity towards the moon because of Newton's third law, but it would not experience the same acceleration because the acceleration of gravity of the moon towards the Earth towards the moon. So acceleration of gravity, or due to, it would be a better way to say that, of Earth towards the moon, having the mass of the moon, and then this distance between them squared. Ultimately, though, it is this force of gravity that is causing the moon to move in a circle around the Earth. When we talk about orbits, the force of gravity is a centripetal force. If you remember, center seeking, a force causing a change in direction. So any object that is being orbited is pulling on a second object, this force of gravity, but the net result is a circular motion. So object 1 is the object being orbited. This one always has to be more massive than object 2. So we could talk about the planets orbiting the sun. Mass 1 would be the mass of the sun. Mass 2 would be the planet. So object 2 is the orbiting object. So we could have the sun be object 1 and the planets be object 2. That would be an example. We could have Earth be object 1 and the moon be object 2. We could have Earth be object 1 and the space station object 2, or any satellite. So there is a variety of options. Just keep in mind that what I'm labeling as object 1 is the object being orbited, and object 2 is the object doing the orbiting. So we can say that this force of gravity is equal to the mass of the object in orbit, so mass 2, times the centripetal acceleration it has. If you remember or look up, we can write this centripetal acceleration in terms of v squared over r. If I come and substitute in for the force of gravity, this universal law of gravitation, so the force of gravity depends upon the mass of both objects. R is this distance from center to center. We call this the radius of the orbit. This radius is measured center to center. Substituting in v squared over r, we find that m2 cancels. The mass of the object that is orbiting, the one that is going in the circle, cancels out. R, one of them cancels, so right now I'm left with g m1 over r on the left side, and then equaling v squared. This v is the speed necessary to be in that orbit. The moon, to have that specific radius from the Earth, the moon has to be traveling this fast. So, for example, let's go ahead and plug that in. So g 6.67 times 10 to the negative 11, the mass of the moon from the test notes, that wasn't the mass, that's the radius, 7.36 times 10 to the 22 over r, not r squared, because one of the r's canceled. The distance between the moon and the Earth, at least on average, was that 3.84 times 10 to the 8th. So the moon, to maintain its circular orbit, this is assuming a perfectly circular orbit, because we're accounting only for the centripetal acceleration, the moon would have to be traveling at exactly 113 meters per second. If the speed changes, coming back to our equation, if the speed changes, the radius of orbit will change. The mass of the Earth's not changing. And so there's always a very specific speed an object has to be traveling at to maintain a specific orbit. Now, realistically, for example, the Earth orbiting the sun. Earth's orbit is not perfectly circular. Oh dear. It's elliptical, And this is not a very good drawing. It's fairly close to circular, but it's not perfectly circular, meaning there's some points in time the Earth is closer to the sun and some points in time that it is farther from the sun. And coming back to this equation is assuming a perfectly circular orbit. But it also helps explain that the speed will change. The orbiting speed changes as the distance from the sun changes. Over here, the speed would be the square root of g, m1 over r again. Keep in mind, m1 means the object being orbited. And so when the Earth is closer, if r is smaller, then v is bigger. If r is bigger, v is smaller. Which we will go through conservation of energy. That's the best way to explain this, is in terms of conservation of energy. But here we have this general relationship allows us to kind of reason through it conceptually. In the test notes, there's no subscript on this m. So you do need to remember, make a note of it for now, and remember that m in this equation is always the object being orbited. And then r is the radius of the orbit.